Hi, good morning, and welcome to the ZP Developer Zone. So we do this every Thursday at 8 a.m. London time, and we use it as an opportunity to answer technical questions that have essentially come in from the week. So, right, so I want to just jump straight into it and answer those kind of questions. So the first thing is I always put this slide up, and we just say, look, we have a ZP Academy. The ZP Academy offers at least a couple of free courses. We have the webinar. We do this webinar every Thursday at 8 a.m. London time. We do collaborations. Now, collaborations, we do sponsor, for example, in the UK, at least 5 PhDs. So we're quite academia facing. We offer jobs, we offer our ZP Developer Zone, and we offer our workshops. Now, I think a lot of these technical questions, we can tend to answer them in these webinars, but if the questions get deeper, then the workshops are the best place to get answers. So we do have a whole bunch of workshops coming up. So for example, we've got workshops, at least 4 workshops lined up in the next couple of months. And I can also see there's an online workshop also booked for February. I just want to say good morning to FTAB. Thank you, FTAB. Lovely to see you this morning. And I will essentially jump into it. Now, if I put a link on a slide, then I'll remember at the end of this to post those links underneath the video as well. So question number 1 is about pH and oxygen sensing for bioprocessing. Question number 2 is around sodium and potassium sensors. Question number 3 is about fingerprinting or basically analyzing chili samples, and I'll discuss that. Question number 4 is inducing an extracellular sort of emission, can I say that, of hydrogen peroxide from cells. I'll talk about that. Cyclic voltammetry at higher concentrations, quite a tricky question. I want to say good morning to Bila, and I'll have a good answer in that this morning, and then arrays of electrodes, and I will discuss that as well. So somebody's looking for a pH and oxygen sensor for a bio product production process. We do have a couple of pH sensors. It's not quite sure which one to use because it really depends. Depends on many factors, to be honest. We've got a couple of them. One of them's made out of ceramic, the other one's made out of PET. And which one you would really choose? I'd actually try both of them and see which one worked best in the actual application of interest. Again, if I put a link in here, then I will definitely put the link underneath the video. If you're going to get a pH sensor off us, you will going to have to sort of essentially test it. So I've also put a link to a couple of test solutions here as well. I would hope, now we always get this kind of results, that you would get pH results sort of like this one, pH 5, pH 7, pH 10. Somebody asked us a few weeks ago what kind of pHs have you tested between, and we've tested between pH 2 and pH 10. I think in most bioprocesses, that's more than adequate, let's say. The other part of the question was about oxygen sensing. So we do have a couple of oxygen sensors. And again, also more importantly, an oxygen test solution as well. Oxygen is quite a tricky analyte to actually, if you do a system and you want to know whether it's working or not, especially for oxygen, it's quite tricky. But so luckily we got a couple of solutions to help you understand whether oxygen sensor is working, and you should get data. And this is the raw data, but this is oxygenated, and then this is deoxygenated, and we can see a quite distinct change in signal. Just want to flag up that in our workshops, we actually do the monitoring of oxygen, and we do a pH as well. So I just want to say those workshops, we actually do those are covered specifically in our workshops. I just want to say, if you're trying to develop a product, you've really got an R&D phase, and then you've got a sort of prototyping MVP phase. I think on the R&D phase, we are definitely now supporting people in their R&D phase using this is a 6-channel instrument. It will allow us to run our biosensors. It's a very R&D tool because you get the raw signal, let's say. Obviously at ZP, a lot of what we do is turning raw signal into meaningful numbers. And maybe I have a video actually later on that will actually demonstrate that. But I just want to say that if I put a link there, that would be the sort of, that would help you come in and find that particular instrument. So this is the the R&D instrument, which allow you to plug those oxygen and those pH sensors in there and essentially get that raw signal. If you're commercializing it, then we have a single-purpose sensor boards, which you can sort of plug into your product. So I've got a data sheet here with a link, and I've also got here a bit of a form factor that don't be intimidated by the size of electronics. These electronics in electrochemical biosensing are tiny. It's one of the big advantages of electrochemical systems is the size of electronics. These electronics are less than 1 inch square, and I've put a link to it there. Now, this question is much more technical, if I could say that. So the person here seems to have some of our sodium and potassium technology. The first question is, why do we need to use OCP, which is open circuit potential? They were asking whether they could use a voltmeter. So I've got a voltmeter, in front of me here. With our sensors, you possibly could use a voltmeter, but I'm not going to recommend it. I'm not going to support it. The reason being is the word voltmeter could mean, this voltmeter, when I bought it, was more like a sort of $100. You can buy voltmeters today that are like $15. So there's such a range of quality in the word, in that term voltmeter, that I wouldn't support it. The higher the internal impedance of your potentiometer or your voltmeter, then the more accurate will be your results. I would say that. But I can't recommend it. I can't support it, though. I suspect they would work, but it's just, if you buy a $15 voltmeter, then it might not work, and then you'll be wondering, is it the voltmeter or the sensor? They're asking here how they actually process the data, and so you do process the data using a Nernst equation, and I'll show you how to do that in a minute. They say here that they have linearity problems. I've looked at their data. I don't think they do have linearity problems, but I will lay that out now. So we're talking about sodium and potassium sensors. This is their raw data. We'll dig into it in a minute. Sodium and potassium, we can see that they get big jumps when they go from 0 to the first concentration and 0 to the first concentration. You can't measure 0 accurately with an ion selective electrode. I will explain that in a minute, but if you go the log to the base 10 of 0 on a calculator or any kind of software, you'll find that you throw an error, and so you can't measure 0. If you want to measure 0, measure something like 0.1, but you can't measure 0. And in biological samples, for example, urine, tear fluid, blood, there's not such a thing as 0 sodium or 0 potassium, so just know, even skin. So 0 is not clinically relevant. Electroanalytical techniques are really covered in our workshops. We spend something like 12 hours, and Aftab, who's online this morning, will vouch for that. We spend a lot of time going through all these methodologies, including potentiometry, which ion selective electrodes are part of. And we've really bulked up now as well our impedance spectroscopy as well. Earlier on, actually, I referred to a single-purpose electronics board. That's actually the board there. So that board can do all of these techniques. Ion selective electrodes, for us, we're often making them by taking one of our screen printed electrodes, functionalizing the working electrode. We have our reference electrode, which is, for example, silver chloride, and yes, we do measure the potential between them. Now, we call it open circuit potential because it really sort of suggests literally that there's so much high impedance that it is open circuit rather than closed circuit, which is when you do have electrical connection between these two things. But we're measuring the potential between these two electrodes using a very high impedance instrument. Yes, our sensors, I think, are actually quite forgiving, and you could use other technologies, but I can't support it and I can't recommend it because, like I say, there's a whole range of quality in these kind of instruments. But obviously, I think the person inquiring is an electronics engineer, so obviously have a go if you so wish. I did a quick processing of their data. So this came in yesterday afternoon. So I had to do a bit of a rush job on this. But yes, it's the Nernst equation that you have to do. Now, I did it using log to the base 10. You can do natural log, which is ln, or they call it sometimes Neperian log, but I did log to the base 10. And I just want to say that you've got 0 in your concentrations. You can't do log of 0. So if you want to have a low concentration, try something like 0.1 millimolar, but don't try 0, and don't plot 0. That's the first thing to be said. So get rid of 0, but then I can plot these three here. So the first thing I did is just plotted them versus essentially signal versus concentration, or voltage versus concentration. And I realized I did it wrong because I didn't do the log. So I did the log of it, and then I did actually go from an R squared of 0.81 to an R squared of 0.94. So I can show I improved linearity just through that. So I think at least on the sodium, it was working perfectly fine. As I said, I just want to emphasize that we did log to the base 10 there. So that came in yesterday afternoon, and I quickly processed it for this morning. We do get a lot of inquiries at the moment about our FoodSense technology. This is a good example, actually, because we're using the electronics that we were promoting earlier on in this webinar. Whereas earlier on I was saying that the R&D instrument will give you raw signal. Obviously, a lot of what we do at ZP is converting raw signals, using things like app development. So this is something that we do as contract development, contract manufacturing. And in this particular video, the method runs and we get a result. So I just want to say that our mindset is not to leave people at the raw signal. It is to genuinely convert them into something that's useful. In this case, this is measuring the hotness of Tabasco sauce, and we've got a Scoville heat unit there of 2,856. Just FYI, it's using the same electronics that I've linked to above. We know that this system is working, if I can put it that way, because actually we are measuring genuine sources, and when people report to them extra hot, or they extra report as sort of pure Naga, we can see the signal increasing in real time. This is the raw signal I'm showing here, as opposed to the Scoville heat unit. It's really intriguing, actually, because we genuinely see the raw signal, whereas so many people, they get these certificates of analysis, they don't see the signal. They just get a number and they think, oh, that must be the truth. And when you really do the analysis on it, it's not the truth. When you sometimes you send something out for outside testing, you get this report with a number. There's no error on it telling you what the experimental error or the analytical error is. You just get a number, and people take that as that must be the truth. Whereas we're quite lucky. We actually we can see what's going on. If somebody tells us it's extra spicy, then we can see literally the capsaicin and see that it is actually extra capsaicin there. I want to go on to question number 4 here, which is somebody's interested in measuring the hydrogen peroxide that's coming. I would call it extracellular. So they have some cells, they expose it to air pollution, and hydrogen peroxide is released. Now that is something that we actually do in a medical application. So we have a very good customer called Exhalation Health. Same electronics, by the way. But what's happening on here is they're actually measuring hydrogen peroxide on the breath, and it's a marker for inflammation. So I think that this person's science experiment is actually linked to this diagnostics device, that by exposing cells, this person is expecting hydrogen peroxide to be released. And the answer is, I think that is the case, as you already know. And actually, it is used in a medical application, and that one that ZP has been instrumental in the design, development, and manufacture of. So that's just a bit of background. If you were to do this experiment, then you would need a sensor from us. These are essentially the cells in that solution. I suspect that you would have a signal. We have to let the signal essentially plateau, and then you can do an exposure of your I would say stimulant, but I know it's essentially sort of a pollution source, which would hopefully then sort of fire up the cells, and there will be a change in signal. So I can see that, what you're trying to do, let's say. So we do have some electrodes, and we do have some electronics. I think the trickiest part is getting our sensor into your cell cultures and stopping things like humidity getting inside of our electrical connections. So I'm not going to deny that there's an engineering challenge for you there. Again, useful links. I will try to remember to put these underneath the video at the end. Question number 5. So we do have some really good Well, we have some educational videos online these days regarding things like cyclic voltammetry, differential pulse voltammetry. But somebody was asking the question, in CV, cyclic voltammetry has a very distinct shape. It's sort of, some people describe it as sort of duck shaped, and we say that there's a depletion that after you've applied a certain amount of voltage, it doesn't matter how much more voltage you apply, the signal's dropping because you've depleted all of the material at the surface. So this person's asking, well, if I just increase the concentration, can I get away from that diffusion limited shape? So I'll show you a paper here, and I've referenced it. The only reason I've done that is because obviously, I want to, if I'm going to use somebody's image, I want to make sure that I've demonstrated where I got it from. So what they're showing here is they've gone from 0.03 millimolar to 60 millimolar. So that's about a 500x increase in concentration. They still have diffusion features, no matter how high in concentration they go. So the short answer is you can't get away from these diffusion features when you're under diffusion control. I'll show you something from our whoops-a-daisy. So here's concentrations going up, but yet they've still got these kind of features, which are sort of mass transport limited features. Let me describe some data from ourselves. This is 1000 micromolar, 500 micromolar, 100 micromolar. If I zoom in here, I've got 10 and 1. So that's the 3 orders of magnitude experiment in terms of concentration. And actually, the diffusional features do not go away. Something that does happen is we get a slight separation in our peaks. So this is due to we're starting to pass so much current that we're getting what's called IR drop. But still, we've got these diffusional features. If you want to get away from diffusional features, it's not about increasing the concentration. It's about how you do the experiment. And so here we have what's called an RDE, a rotating disc electrode. So if you do voltammetry and the electrode is static, you get something often that looks like a CV. If you actually rotate the electrode, by the way, I did my PhD on rotating disc electrodes. I don't recommend them because I really feel like they're of academic interest, and I don't feel like they really move, let's say, the industrial applications forward. I think they hold people, in the beauty of the information you can get from them, but they don't really move you forward in terms of making products for the real world. So that was my opinion. Now what's going on here is at 100 RPM, so if you're rotating at 100 revolutions per minute, I'll just move myself out of the way, you still get that diffusional feature. But when you then increase the rotation to 1500 RPM, the diffusional feature goes away, it plateaus. And so if you want to overcome this diffusional feature, it's not by increasing the concentration, it's actually by increasing the mass transport, by stirring, flowing, rotating. But anything that pumps material to the electrode is how you overcome that diffusional feature. I do dig into this for quite a long time in our workshops. So these slides are taken from the workshop, just snapshots from the workshop. Just finally, somebody inquired, can you do a something like 96 electrodes in a small area? We can do that. We do have that kind of technology. We design it using PCB technology. Be careful if you try to use PCB for biosensing. It won't work. We have to come up with some proprietary processes to make PCBs actually work with electrochemistry. Otherwise, you get terrible corrosion events. So question 1, pH and oxygen sensors. So I've shown and linked to pH sensors. I've shown and linked to the calibration solution. I've shown and linked to an R&D instrument. And I've also shown you an instrument that is, or a circuit board that you should be able to use in your commercial applications. Sodium potassium sensors. So, yeah, you can probably use these, but I can't support it. I can't recommend it because I can't control the quality on on voltmeters. But your data, especially, well, I've looked at the sodium data. Your data makes perfectly good sense. So I have processed it. I showed you I processed it in a Nernstian fashion. We are fingerprinting chilli sensors, and we can definitely see the capsaicin directly in those samples. Your hydrogen peroxide experiment, that is done in a diagnostics application, and I've tried to describe how we would do that experiment. Cyclic voltammetry at higher concentrations, you just get more and more peak, but you don't get away from the diffusional limitation. And if you want to get away from the diffusion limitation, control and increase the mass transport, stirring, mixing, flowing. Arrays of electrodes, sure, we have lots of electrodes using PCB. So I have spoken rather fast this morning, but you can see I wear my shirt. We have meetings kicking off pretty soon, so I have to jump into them. If you've got any questions, the questions have already started coming in. We will cover them next week in the webinar. If you've got questions on top of questions that you've seen answers to this week, send them in and we will try and deal with them next week in the webinar. Okay, take care and have a good week. Thank you very much.